Look at this beast, a triple E-class container ship, 400 meters long, weighing over 200,000 tons. It's essentially the Empire State Building lying on its side, cutting through the ocean with massive kinetic energy. Once this colossus starts moving, it seems like nothing on Earth could stop it, let alone change its direction. And yet, to steer this monster, all we have is a single plate of metal sitting quietly and humbly beneath the cold water at the stern. It's called the rudder. Would you believe that its surface area is often just 1/60th or even 1/70th of the ship's underwater profile? To put that in perspective, it's like trying to steer an 18-wheeler truck just by sticking your hand out the window. So how? How does a tiny piece of steel overcome the inertia of hundreds of thousands of tons? The answer isn't about brute force. It's not about just blocking the water. It is a story of underwater hydrodynamics, of inverted airplane wings, and a quiet engineering revolution that has spanned millennia. Today, we are diving under the stern to deconstruct the marine rudder, from its history and insane physics to the internal anatomy you've never seen before. Welcome to the world of marine engineering. Let's dive in. Before we had steel titans, our ancestors faced the ocean in wood. Ancient Egyptians or Vikings didn't have a rudder in the center of the stern like we do today. They used something called a steering oar. And here's a fun fact you might not know. Because most sailors back then were right-handed, this massive steering oar was always tied to the right side of the stern for easier handling. In Old English, the steering side was called steerboard, and that is the origin of the term starboard used for the right side of a ship today. Naturally, because the right side was blocked by this giant oar, when they docked, they had to tie up on the left side to avoid breaking it. The left side faced the port. That is why the left side is called port side, a 1,000-year-old convention born simply because of where they placed the oar. But the steering oar had a fatal flaw. It relied on pure mechanical leverage. In rough seas, waves would smash against the oar with tremendous force, often throwing the helmsman across the deck or snapping the shaft entirely. By the 12th century, a revolution sparked in Northern Europe. They invented the stern post rudder, a rudder attached directly to the stern post using iron hinges. This was the turning point. Instead of using human strength to row against the water, we started learning how to harness the flow itself. Now, forget everything you think you know about rudders acting like paddles. If you think a rudder simply turns right to block water and push the tail left, you are only half right, and that's the inefficient half. In reality, a rudder is a vertical airfoil, and it works on the exact same principle that helps airplanes fly, Bernoulli's principle. Imagine we are underwater. When the rudder is straight, neutral, water flows evenly on both sides. Pressure is balanced. The ship goes straight. But when the captain orders a turn, say 20 degrees to starboard, what happens? The aerodynamic shape of the rudder forces the water on the left side, the suction side, to travel a longer distance to meet up with the flow on the right. To do that, the water on the left must speed up. According to Bernoulli, as velocity increases, pressure decreases. Conversely, on the right side, the pressure side, the water is compressed, slowing down and increasing pressure. The result? A massive pressure difference is created. One side sucks, the other pushes. This creates a powerful resultant force called lift. This lift force pushes the stern to the port side, and since the ship rotates around a pivot point, when the stern goes left, the bow swings right. However, physics always has limits. Why is it that in movies you hear the captain yell, "Hard to starboard," but the rudder angle indicator stops at exactly 35 degrees? Why not turn it 90 degrees to spin the ship like a car? This is a critical limit called the stall angle. Water has viscosity. If you turn the rudder too aggressively, past 35 degrees, the water flow can no longer stick to the surface of the rudder. It detaches. This phenomenon is called flow separation. Instantly, the area behind the rudder becomes chaotic, filled with turbulence and cavitation bubbles. At this point, the lift force vanishes completely. All that remains is drag. The rudder stops steering and becomes a giant brake. The ship won't turn. It will just slow down and shudder violently. That is why 35 degrees is the golden rule in standard rudder design. Crossing it spells disaster. So, how is this underwater wing built to withstand hundreds of tons of pressure without snapping in half? Let's crack it open. The heart, or rather the spine of the system, is the rudder stock. This is a massive, solid, forged steel shaft, sometimes over a meter in diameter. It penetrates from the steering gear room down to the ocean floor to hold the blade. Its job is to transmit torque. Next is the rudder blade. Don't let its bulky appearance fool you. It's not a solid block of steel. If it were, it would be too heavy and sink the stern. It is hollow. Inside there is a complex network of steel ribs and stiffeners, just like an airplane wing, covered by thick steel plating. This hollow structure also creates some buoyancy, helping to reduce the load on the bearings. And how do we turn that massive stock? Welcome to the steering gear room, the muscle of the ship. Here, hydraulic systems generate immense pressure, driving giant rams pistons to rotate the tiller. And according to international maritime law SOLAS, this system must have redundancy. If one pump fails, the backup must kick in immediately, within seconds. Losing steering in the middle of the ocean is a nightmare no captain wants to face. Not all rudders are created equal. Depending on the vessel, engineers choose different weapons. First, the unbalanced rudder. Imagine a door in your house. The hinges are at the very edge. The entire area of the door is on one side of the axis. This type requires huge force to turn because all the water pressure fights against it. Today, it's almost extinct on large ships. The industry standard today is the balanced rudder. Engineers used a clever trick. They moved the axis inward. About 25 to 30% of the rudder area is actually forward of the pivot point. Why? When you turn, the water pressure on this forward section actually helps push the rudder further into the turn. It acts as a counterbalance, significantly reducing the load on the hydraulic steering gear. Simple, yet brilliant. But the pinnacle of technology is the Becker flap rudder. Look closely, it has a hinge. When the main blade turns, a smaller trailing edge, called the flap, automatically angles even further thanks to a mechanical linkage. The result is a perfect aerodynamic curve. It can generate 50% to 90% more lift than a standard rudder. Ships equipped with this can turn almost within their own length without tugboat assistance. There is a secret that every veteran captain knows. The rudder is almost useless without its partner in crime, the propeller. The rudder is always placed directly behind the propeller. This is not a coincidence. It is there to catch the high-speed water flow, called the propeller wash or slipstream. The faster water flows over the surface, the stronger the lift. This leads to a pro-maneuver called the kick ahead. Imagine a ship drifting very slowly. The rudder has almost no effect because the water flow is too weak. The ship won't steer. In this situation, the captain orders hard over and then blasts the engine power for just a few seconds. The propeller spins up, shooting a jet of high-velocity water directly onto the turned rudder. The stern is instantly pushed sideways by the sudden lift, even before the ship itself picks up any forward speed. That is how giant ships maneuver in tight harbors. They don't steer with ship speed, they steer with propeller wash.